Okay, so make a note here with this temperature to remind yourself. Okay, that temperature, right, is the average kinetic energy or movement of molecules. If temperature goes up, that means the molecules are moving faster. If temperature goes down, the molecules are moving slower. Okay? Temperature changes indicate there's an energy change, but energy is not in the unit of Celsius and Fahrenheit or Kelvin, right? So those are the units of temperature, right? We have like degrees Celsius or Kelvin are our key ones we'll use. Energy, the main units we're going to use here is energy is in a unit of something known as a joule or a kilojoule. We're just converting into kilos, okay? That's going to be one of the main units we use in this unit for energy. To relate it to something you're maybe more familiar with, there's a direct connection between this and the unit of a calorie. Calorie is a unit of energy, hence food has a calorie assigned to it because it's how much energy does it give our bodies, right? So we can convert everything we're doing into a calorie. It's not often the way we represent it in this type of chemistry, but in other chemistries, right, nutritional chemistry, it's the only energy they use, okay? Now, we talked about these two words before, endo and exo. All right, too much side talking here. Okay? Thank you. Endo and exo as the process of heat changes. Today, this is really going to be our focus, and all of your homework today is going to be that. It's going to give you something, and you're going to say that's endo or that's exo. So we're going to look at these in a lot of different ways, but how they represent. First thing, though, we have to understand, because of the law of conservation of energy, if one thing is releasing the heat, then something else is absorbing the heat. So it can be a little tricky with endo and exo, because technically there's always both. If one thing is exo, there's something else near it that's endo. So we have to make sure we're focused on the right process. So we're going to do a little, thing here to kind of get us in the right mindset of understanding heat transfer if it's a new thing to you. So what I'd like you to do is pick your favorite hand and raise it in the air. Get a good stretch. I pinched my shoulder this morning, so I really need to stretch. Okay, now take your hand and reach down and grab the leg of your chair. Feel it. Observe. Okay. Now, depending on the individual, it might feel different, but most people would say it feels cold. Once again, a few people it might feel warm, but most people, the metal of the leg of your chair feels cold. Now keep your hand there, keep holding it. Okay? So as you're holding the leg of your chair, everybody, and it feels cold, okay, so imagine this is the leg of your chair, right? You're holding onto it. When something feels cold to our hand, that's because the heat is leaving my hand and going into the chair. So it feels cold. Because heat is leaving my hand. If heat leaves me, I'm going to feel cold. If I go outside in the winter, I feel cold because heat is rapidly leaving me. One thing about heat is heat always flows from high to low, or warm to cold, always. Cold is, once again, not a measurement. Like, it doesn't exist in the scientific world, right? Only heat does. So cold, we always say, is like the lack of heat. Okay, as you're holding it there, how does it feel now in comparison? Warm. Yeah, because it's equalizing. The heat always wants to try to equalize itself. And so if your hand is warmer than the chair, heat will continue to flow from your hand until the chair is the same. Now, the only way that this works for us is because we're a living person and we produce heat. The chair doesn't produce its own heat. It just adapts to whatever environment it's in. Okay, all right, take your hand off. Now, take the other hand. Sorry, Scott, you don't. And touch the top of your table. In comparison to the leg, how would you describe it? Some people say the same. Some people say, I'd say most say it is a little warmer than the leg of your chair, is how most people would describe it. The fact is, they're in the same room. My battery died, but I have a laser thermometer, and I normally show this, so take my word for it until I get new batteries, but they're the same temperature. The temperature of this is the same as the leg of your chair because they're in the same environment and they're not living, and so the heat is going to be the same. Why, by raise a hand, anyone have an idea, why do they feel different though to us? Anyone have an idea? Yeah, Levi. So the other thing to consider with heat is conductivity. Some substances transfer heat, which is conductivity, much quicker than others. Metals are a great conductor. They transfer heat very rapidly. And so that's why when you touch it, the heat transfers quickly versus other substances that do not. This is why we cook with metal pans, is because we want the heat to transfer quickly, right, from the burner to our food. Same reason if you're in your car in the summertime, right, and your car's been parked outside, and you go into your car and it's hot in your car and you go and touch the metal part of your seatbelt on accident, right, and it like burns your fingers. But if you touch the fabric part, they're technically the same temperature. The difference is the metal is just slamming you with the heat all at once. So there's kind of two components to think about when you're thinking about heat. Is number one, like the actual temperature of the substance, but number two is how well it transfers the heat. Okay? Yeah, Ian.
So like if you had like a dashboard of a car and your seatbelt that's metal, if you touched yourself with the metal it would hurt instantly, but if you put your hand on the dash for a while would it hurt?
It could. It also, because if it's so slow, then it kind of like, it's not going to burn you because it like dissipates the heat. Does that make sense? But it could over time feel more painful if you left it there. Because it's the whole idea of like the energy that's getting put in, right, is coming, with the metal it's coming all at once, which then can...
So then the dashboard would just let it out?
Yeah.
Same amount of energy.
Yeah, same amount of energy though. So, does that make sense? Yeah, great question, Ian. Zach?
Well, this kind of backtracks a bit, but if our bodies produce heat, but the energy also can't be created or destroyed, where does our bodies get the heat from?
Great question. Yeah, through the reactions in our body. So the chemical reactions of our body, primarily food, is where we're getting our energy. Because we're warm-blooded, it's a little bit different if we were cold-blooded, right? But because we're warm-blooded, we use the energy to make our heat. Does that make sense? Good question. Ian and Zach have smiley face for this, by the way. Yeah?
So does that mean if you need muscle to be like cold?
I don't know for sure, but I'd say hypothetically yes. Right? Like if you, like, because your body's going to have less to use. I mean, you have other sources if you don't have food, right? It'll start eating your fat and your muscles, right? So like it can start burning those things. But, yeah. Okay, final factor, and then we'll keep going here. Don't say it out loud. Everyone think in your head, and then I'll have you share with your table buddies. Close your mouths. Don't say it out loud, but think in your head. What is the point in terms of talking about heat transfer of coats in the winter? Don't say it out loud. What role does a coat play in this process? Don't say it out loud, but think to yourself. All right, turn to your, you can talk as a whole table. Talk as a table of the role coats play. Ready, go. Okay, Brian, I really liked how you said it. Will you share with everyone what you said of what role coats play?
I said that it just keeps the heat already produced from escaping.
Yeah.
So normally if you weren't wearing a coat, all your heat would be able to escape really quickly, but it just kind of keeps the heat already produced. Supposed to be, I guess.
Perfect, good, have a smiley face, right? Because heat always flows in which direction? High to low, right? So if I go outside right now, it's way colder out there than my body is. So the heat from my body is naturally going to start to leave me, right? I wear a coat to try to keep, the heat's still going to come off my body. But it keeps it in, and it also makes then the difference between the two environments not as much, and so my body won't keep releasing as much heat. If you go out without a coat and you just don't put one on, your body will just keep releasing the heat until you have no more heat to release. It's called frostbite.
Is it like reflecting the heat back at you, or is it just like acting as an insulator?
Great question. I would say, and this is, someone asked this last period, and I'm not entirely like confident in my understanding of heat reflectors, but this is my best understanding. I'd say most coats don't reflect the heat. They just insulate it, trap it, try to keep it from leaving, and once again, if the inside of my coat is warm, then my body's not going to keep releasing as much heat, right? There are certain materials, like in marathons, people wear those like metallic-y thin, like they're super thin, but they're like a blanket. Just nod your head if you know what I'm talking about. So okay, right? So those I think do work in somewhat of a reflective way, which is why they don't have to be super thick, right? So I'd say that there might be some coats that have some of that built into it as well, but I don't know if most coats do. Yeah, good question. All right, any other questions as do we feel like we kind of we're visualizing heat, right, and how it works? Yeah, Porter.
I was just wondering, because like, if I go outside and I put on like 18 hoodies or something, I'll get like really hot, and is that not, because if it's just insulating the heat and my body would stop producing heat like at a certain point, why do I get like hotter?
So let me put it this way. Great question, Miss Maybe. So let's switch it. It's not wintertime outside. It's summertime, right? Let's say we're in Mesquite, 120 degrees. That's hot. Okay, so you go outside at 120 degrees. Now, in a sense, the opposite is happening where your body, because of the heat always flows which direction?
High to low.
High to low. So now if the outside environment is higher than my body, then heat starts flowing into my body and makes me feel hot. Does that make sense? So in a sense, same thing if you wear too many layers, right, then the heat starts going into your body, and then you get too hot. And then that's called heat exhaustion, right, over time. So does that make sense? Yeah, good question. Did I see a hand over here? Yeah, James.
How come when you exercise, even if it's colder than what your body is, then you still can get hotter?
Great question. So where's our heat coming from?
The chemical reaction.
The chemical reaction inside of us. So when we exercise, we increase those chemical reactions. And so if you have more chemical reactions, you produce more heat.
But then what is it going out to?
So it does leave us, right? Like in the process, but it's like heating you up. And then but it can't like exit you quickly, I guess. Like we're not like metals and we can like dissipate our heat quickly. And so if you produce a whole lot, it still takes time for it to. And then that's also like your body's sweating is like a natural way of it trying to cool itself down because you've raised it up. Does that make sense? Yeah, great question. Any other questions about this idea of heat flow? Okay, the other way, and then we'll look at the next slide here, as you think about heat is often a payment. Okay, I think of heat kind of like chemical money. It's the payment needed to make a process happen, or the payment that is given because it did happen. Okay, so let's look at endothermic first, and then we'll go to exo. So in an endothermic process, we learned these words a little bit last unit. Draw in the air for me. What does an endothermic graph look like? Draw in the air. Do you remember what an endothermic graph looks like? Draw it in the air. There we go. I think we're on the right page. Some of you guys are adding some extra details. I don't know how to say it. All right, if you do something like this of low to high, how does it smile? Okay. Slide this down so I can find it. Okay, so with an endothermic process, we've already learned how to identify it from a graph. Today we're going to learn 3 other methods, and this is what your homework is an example of given something you should be able to identify it's endo or exo depending on what's given. So the first way outside, so the graph is the first way. If you see a graph, you should be able to know, oh, that's endothermic or exothermic based on this one ended higher than it started. Okay? The second way that you should be able to identify endo and exo is from the overall change in heat. Okay, so remember delta means change. H is technically not heat. It's called this thing called enthalpy. So this is change in enthalpy. But enthalpy is really the fancy word of heat. So it's nice that they used an H to represent it because you can think of it as the heat energy. Okay, so this is a change in enthalpy. If the change in enthalpy is positive, emphasize that here. By the way, reminder, you can use the highlighters whenever you want. I made the note single-sided again, so if it bleeds through, it doesn't mess up. Okay, but if it is positive, that means heat went into the system. Now keep in mind, this is not the same as temperature, because this heat, in a sense, is being paid. It's being paid to make something happen. Not, maybe it could be to make the molecules move faster, but more often it's being paid to break chemical bonds. So breaking bonds is an endothermic process. It costs money to break a chemical bond. Right? So if these two markers are chemically bonded to each other, I have to pay a certain amount of energy for them to exist like this. Okay? The third way you could see it is sometimes they write it as delta H equals. Other times they actually put the energy within the equation. So notice here's a second example, or third example here, where the kilojoules, circle this right here, is within the pluses and the arrows. When it's placed within the equation, it's all about where it lies. Endothermics, heat is a reactant. You have to pay the heat. You need this plus this for it to become that. Endothermic means the heat has to be paid, so it's going to be within the reaction itself. So notice kind of the similarities, but the differences of these two things. If it says delta H equals, you're looking for the sign. If it doesn't say delta H equals, then you're looking for where is the kilojoules in the equation. And we'll see exothermic in a second, which will help you see the opposite side of it. Okay? All right, questions on the reactions? Yeah, Brissa.
So if that one was written like that one, it would be negative 28?
Say that one more time.
So if that one was written like that one, would it have a negative in front of it?
No, so this is still endothermic
Okay.
because it's a reactant. So so all these examples are all endothermic.
Okay.
So if this one were written like that one, good way to visualize it, it would just say delta H equals 28 kilojoules. Does that answer what you're asking?
Yes.
Yeah, great question. I was my face that. Alex.
How do you define a system? Like what exactly? I mean, it probably could be a bunch of different things.
Yeah, in our case, most of the time the system is the chemical reaction. So it's like when I pour these two things together in the beaker, which we'll do some demos here in a second, that is the system. The surroundings would be my hands, the air around it, everything else. Technically, it could be anything, like in our case with your hand and the leg of the chair, the system is whatever you choose to call the system. Because one thing, so when I grab the leg of the chair, where was heat flowing? From my hand to the chair. So if my hand is the system, I would say it is exothermic, because heat is leaving my hand. But if the leg of the chair is my system, then it is endothermic. Does that answer your question?
Yeah.
Kinda. And that's where it's easy, because it's like, oh, 50-50, but that also is what makes it tricky, is because depends on where you focus. But in our case, I would always focus on, whenever I read a problem, I visualize, that deals with endo and exo, is I visualize myself holding the beaker, right? And if I'm holding this beaker, after I mix two things around in there, and the beaker feels cold to my hands, what does that mean about the system? Is it taking in heat or releasing heat? It's taking in, because it feels cold to my hands. So that's how I always visualize it, I used to later when I take some tests, I'm a very visual person, so I'd like go like this, close my eyes and think, okay, I got it. So, does that help?
Yeah.
Okay. Yeah, Levi.
So on the example, so if it says like delta H, is that, oh, sorry, one second. Is that saying that it's on the left side if it's positive and on the right side, or is it on the right side if it's positive?
Whenever it has, if I understand your question, Levi, whenever it has this equal part, this could be placed on either side of the equation. Because it's not putting it within it, it's just saying, hey, for this equation, delta H equals this.
Okay, but then with the second one, when it says, because would that one be exothermic?
It's still endothermic, so this is putting it within the equation, right? Because it's a reactant, it's saying heat is going into the system.
But then it's not coming out, so.
Because what does endothermic mean?
Oh, wait.
There you go.
My bad.
No, you're good. And that's another thing why it can be so easy to flip-flop them. So, okay, by raise a hand, can anyone give me a real-life situation that you could deem as endothermic, as an example? Smiley face, anybody? Give us an example. Jack.
Put food in the microwave.
What do you want to cook in your microwave?
A burrito.
Okay, cooking a burrito. Okay, Jack, why is cooking a burrito in a microwave an endothermic process?
Because it absorbs the heat and then
Yeah, right, so the heat is going into the burrito, causing it to be cooked, right? Endothermic. Good, how was my face? Someone else? Cooking a steak. We're being repetitive, but Jonah, tell us, why is cooking a steak an endothermic process? Right, the heat goes in to make it go from raw to cooked. Good, which is a chemical change, right? All right, let's hear one more non-cooking example, maybe?
Oh,
Okay, what was your cooking example?
I was gonna say baking a cake,
Baking a cake. Oh,
because it rhymes
That's not,
too.
hey, that's not
oh, cooking a steak, baking a cake.
Think about that. Yeah.
Okay, have a smiley face.
Let's go.
Now with this, and then we'll get. Do we have one non-baking examples? Okay. Tell us one more time why would be baking a cake an endothermic process?
Because you put it in the oven and the cake. I don't know.
Where's the heat flowing? Talk about the heat
It
flow.
goes from the oven to the cake.
Yep. So right, the heat's going into the cake, changing it chemically speaking, right? Sometimes it can be a physical change, but in our case, it's a chemical process that's happening, right? Now, while the cake is in the oven, right, it's going to be hotter. But once I take it out and the process has happened, is the cake higher in temperature because of the heat that went in? What is that heat being used as it goes into it for? It's payment, right? Like the heat doesn't just reside in the cake forever. The heat gets used, and then in a sense, it's not gone because it's not destroyed, but it gets converted into the molecules themselves. So sometimes if you're wondering, like, well, where's the heat going? Sometimes it's using to be paid to make something happen, right? In our case, what do we have to pay? We have to pay to break the bonds. So when something is endothermic, you're paying the heat to break the bonds. Okay, one more in the back.
Drying your clothes.
Good. Why would that be endothermic?
Because you're transferring heat into it, so the water molecules will be released.
Perfect, right? So we're trying to, in a sense, I'm going to even add, right, evaporation is an endothermic process, right? To go from a liquid to a gas, heat has to go into the liquid to get them to move faster, so they have enough energy to break the IMF, so those are the bonds we're breaking, right? IMFs also count when we're talking about breaking bonds, right, for it to turn into a gas. Okay? Yeah, Porter.
I'm just a little confused about the breaking bonds part
Yeah.
of endothermic. I was just wondering, like, if I were, for example, like splitting the atom, is that an endothermic reaction?
No. Well, no. So, it's splitting of an atom is different. It's not a chemical process. It's a nuclear process, right? Because you're not splitting atoms, you're splitting protons and neutrons. And so there's kind of a little bit of a difference in there in that when you split an atom, I guess it's similar in the sense of like all molecules and things, like they have potential energy stored within them. Atoms have a lot of potential energy. And they have this thing called the nuclear binding energy that holds a nucleus together. And so when an atom splits, that nuclear binding energy is the atomic bond that comes out.
So chemical reactions just don't have they don't have that super.
Yeah, it's that so let me tell you this and see if this helps in our discussion. So just like breaking bonds is endo, forming bonds is exo. So when a new molecule gets created, because it's more stable, because they wouldn't create it if it's not more stable, right? The only reason molecules come together is because it's a better arrangement than it was before, right? When that new arrangement is achieved, because it's more, so if they're like up here, they're individually, they have this much energy, but together they have this much energy, that excess energy comes out in the exothermic process. So it's kind of similar in that way, but it's also a little bit different in that splitting a nucleus doesn't really make it more stable. It actually is like just almost makes it like crazy. Well, it kind of depends. When you split, depends on we're splitting hydrogen or we're splitting a big one. Because when you split like uranium, which is the typical element in like an atomic bomb, right, is uranium, it actually is becoming more stable because it's a very radioactive, big, unstable nucleus. And so when you put it apart, that lower stability than all the other gets released. So, does that make sense?
Yeah.
And you actually, I don't know if they've ever really, I don't know if you can really split hydrogen. Because a hydrogen bond isn't splitting, it's fusing. So a hydrogen bond, which is bigger, is the process of coming together, not splitting. Great question, reporter. I wish we had time to talk about nuclear in AP. After the test, we can if you guys want to for fun. So, yeah, Alex.
I mean, like for one of those examples though, like it would still take energy to split apart like an atom or something like that. So you're still using energy to create an exothermic reaction, right?
So do this for me. What's an exothermic graph going to look like? Good. So like something like that, right? So draw an exothermic as an example. So in an exothermic process, notice there's still an uphill, right? Like there's still an amount of energy, because keep in mind energy is our y-axis. Even in exothermic, a certain amount of energy went in. The reason why we classify it as exo is that the amount of energy that came out was a lot more. And so yes, even in an exo or endo process, you have ups and downs, right? Even in endo, there's still a downhill, but the difference is kind of the overall energy change. Does that kind of make sense? So as we're looking at that, let's add that here. So keep in mind, so forming bonds is exothermic. Okay, when a new bond forms, it's always going to be exothermic. But overall, most chemical reactions have both going on. Some bonds are breaking, some bonds are forming, so it's just a matter of the energy difference. Okay, I'm going to slide this down so I can highlight with you here. So once again, exothermic, the difference here now is that the delta H, right, emphasize here, highlight, the sign. The sign is negative, which is telling you the direction of the heat, right? Negative heat just means heat is coming out, right? It means heat out. Just like there is no such thing as negative money, there's no such thing as negative heat. So you can be in debt, but is there a tangible thing that is negative? So it's the same idea, right? We can have negative heat because it's telling you which way is the heat going. Out. If your bank account is negative, which way is your money going? Out, right? So it's the same concept here. If it's telling you the direction of the flow, but there's no such thing as like, I can't give you negative 300 joules of heat. Like that's not a thing that can be given. It's releasing 300, the negative is the direction. So then in a reaction is now, notice that it's written as a product. So if it's exothermic, the heat will be on the product side, but notice that it's plus because heat can't be negative, right? But being over here is indicating, hey, when this and this react, it's going to make this plus this heat, right? This reaction is going to make that heat. which tells me overall that there's more bonds forming than there were breaking, because overall more heat was released. Okay, questions on exothermic before we get some examples? Okay, raise a hand, smiley faces, give me some life examples here. Caleb.
Hand warmers.
Hand warmers. Why is a hand warmer exothermic, Caleb?
Because it produces heat.
Yeah, right, so hand warmers are some type of chemical reaction. We'll play with some next period actually, right? But often, like if you think of like the black ones, right, you shake them, you're mixing the chemicals together. As the reaction occurs, heat just comes out, right? Good. Example of my face for that. Bryson.
Why?
Fire. Why is fire exothermic, Bryson?
Because it's hot and it goes everywhere.
True, it is hot. Now this is a great example with exo. Does fire require an ignition? Yeah. But once I get it going, right, once I put a match to my pile of wood, if I've arranged it nicely, do I have to keep adding heat? No, right? So you need the little uphill to get it started, but then as long as it has fuel, it will continue to burn. Yeah, Aglia. Oh, perfect. So like us taking an ice bath would result in you becoming, like it would encourage your exothermic even more. Yeah, good one. I'm going to put with that, because it relates to it, is actually the process of freezing anything. I'm going to put freezing water, right? Or in a sense, the process of going from a liquid to a solid is exothermic. Because once again, a lot of times I think if it's a molecule example, I think about the movement, right? Liquids are moving like this. And so if they're going to become a solid, they have to slow down and bond IMFs, and so that energy actually gets released. So when you freeze something in your freezer, the reason why your freezer has to be like plugged in is because stuff freezing in there is releasing heat. And so it actually has to like constantly be keeping that from warming it up. So, Alex.
Baking soda, vinegar, volcano.
Good one. Yeah, and that one's maybe not as like, that one might be more like you just kind of have to know from life example, right? That like chemical reactions. I'll actually add that any acid-base reaction, which is actually exothermic. All acids and bases when mixed, when they neutralize, they actually are always exothermic. Go ahead. Have a smiley face. Actually, I have a smiley face. I didn't say that. All right, Gavin, let's hear one more.
Would it be like Mentos and like Coke then too, or whatever?
Yeah, because that's also an acid-base reaction. Yep. Yeah, the Mentos and the soda can as well. Yeah. Good question. So electricity is different than heat energy. We actually have a whole different classification of when it's dealing with voltage, where it is similar, like there's a different terminology we use that we'll get to in Unit 9. But yeah, so it's similar, but we reserve endo and exo for heat transfers, not all energy transfers. So
Doesn't electricity transfer heat?
as it's run, so there's that process, yes. Mm-hmm. So there's a component of both for sure.
Okay.
So yeah, good question though. Okay, let's take a look here, and then I gotta make sure we have time to pass back your test. What time are we doing class? 15. Okay. Let's look at these graphs and then we'll go through our demonstration. Skip that demo real quick and go to the graphs. We already talked about these, but I just want to emphasize it, and then we'll do our 2 demos to wrap it up. So we already drew some of these, or you maybe did, but if not, here they are. Okay? So when we're looking at these processes, once again, overall, this would be classified as endothermic, right? And overall, this would be classified as exothermic. But once again, notice, right, there's a climb and a decline in both, right? So the process of going up would be the process of breaking the bonds. Right, so this is, okay, we need that much energy to break the bonds. And then this is the energy that got released when the bonds formed. So when something is overall exothermic, we would say that there was more energy released from the bonds forming than the energy needed to break the bonds. And then of course vice versa for endothermic. Questions on this idea of connecting? So this is where I'm trying to connect what you see with your eyes, right? You see this, you see the heat, we can't see the heat, but you can feel the heat. But what does that mean about the molecular level? Yeah.
So for the other side, it's just like it would be like the same order, but like energy.
Yeah, so it's still always breaking bonds going up, always forming bonds. But the difference is this one took more
Once you break the bond.
than what was formed. Yeah. Okay, we're gonna do 2 demonstrations here, and your job is to identify if it's endo or exothermic and have a justification of why. Okay? With our justifications, we are definitely improving from the beginning of the year on our FRQs with our justifying, but there's still some work that can be done before the end of the year to making them perfect, right? Because that's how we want them to do when we take the AP test. Keep in mind when you write a justification, right, it's not about having lots of words, right? You want to keep it as simple as possible, but you also want to make sure you create a clear picture to the person reading it of like your understanding, right? Number one, some of us need to stop writing your answers as if you're writing them to Miss Alviso. Okay? Imagine I am somebody in Louisiana who has no idea who you are, what you've done in class, what you've learned, and you've got to make sure you write it that way. So don't, some of you guys like reference specific like things we did in class, right? Like ghost was one example, but on this test there was people who talked about like the fire demonstration, but they just said that, they just said, oh, it's like the fire demonstration. Right, like you can use it, but you got to make sure to create that one. Okay? All right, demo number 1. Ready? As you decide whether it's endo or exo, you can decide as a table, but like talk quietly so like others don't hear. Okay, so the first demonstration I have is I have some water here. I have a thermometer just as to help us observe what's going on. It's right now at 19.3 degrees Celsius is the temperature of our water, 19 Celsius, yeah. Okay, I'm going to add some ammonium nitrate to our beaker, okay, and this is going to be more of a physical process because it's just going to dissolve. So it's not reacting with the water, it's just dissolving. Flip to the front page of your notes and you'll see this example. So here's our before equation. So we have, not ammonium chloride, sorry. So you already have this in the second box. You have ammonium nitrate, solid. It's breaking up into ammonium and nitrate ions. Okay, in this next box right here, it talks about the molecular view. So what's going on at the molecular view when I add this to this, how is this becoming that? What's not in the equation that's helping this process? The water. Remember, water plays a key role because it does. So in your molecular view box, if we have NH4 plus by itself, what's actually surrounding it? And in what orientation? Since this is positive, there you go. So the oxygen, so draw this in your molecular view. Right, and then our NO3 is negative, so you should draw your Mickey Mouses the other way. Okay? This ringing a bell? So let's identify and then we'll do the demo. Are bonds breaking in this process? So what bonds are breaking? Yeah, together, apart, right? So this right here is a bond broken. Have smiley face, Brissa. Are there bonds forming in this process? This, IMFs, right? Remember, count as a bond interaction. So this is bonds forming. So we have both bonds are breaking, bonds are forming. Now we're going to see which one is outweighing the other, I guess. Okay, this isn't the most exciting, but it'll get us started in our visualizing because it's just something dissolving. But you got to start somewhere. Where's my research?
You really got.
Alright, so we're adding some ammonium nitrate. It looks like Dippin' Dots. It's a very toxic Dippin' Dot. So, alright, give it a stir.
Pick up that one.
Okay, so once again, your goal now is in that final box right there. I'll tell you what our thermometer says, but you're supposed to tell me, is it endo or exothermic and why? Okay. So it's not all dissolved yet. So we're at, what did I say, 19.9? What did we start at? 19.8?
I don't remember. I don't remember that. Don't trust what I said.
Well, we were at 19 something, and now we're at 18.2. So I guess no matter where we started, well, we know the temperature's gone down. So talk to your table buddies quietly.
What up, butters?
And decide, is this process exo or endo and why? Oh, perfect. At the end of class. Yes. Yeah.
I got it. Where did you get that?
Okay. Have we enough time to discuss this one? So I'm rushing. Are we ready to do the next demo? You need another minute? Okay. Bring yourselves into the lab for demo number 2.
Subscribe.
Is that an option? I can be awake.
Yeah, what the heck, bro? That's a horrible idea.
If someone said that was you, would you agree?
Yeah, it's like it takes effort.
I just left the camera filming. That's what does. Sorry, people at home.
It was really cool just seeing your mouth.
Sorry about that.